Welcome to SIMNET, drone design and simulation powered by the cloud. In this tutorial, you will learn how to model a quadplane VTOL from scratch. This includes modeling its airframe and propulsion system, adjusting its mass estimation and setting up its flight control system. Let's get started. For this tutorial, we will model an existing electric quadplane called the Pegasus 230. We will load front, top, and side images of the aircraft to use as references. Use the editor pane to add a reference image component. Name it front image and upload a frontal picture of the aircraft. The image must be scaled to the correct size. To determine the correct scaling factor, use the viewer pane's measuring tool to measure the wingspan. The wingspan of the actual aircraft is 230 centimeters, while the wingspan in the image is 336 centimeters. Therefore, we will scale the image by the ratio between these two values, which is 0.684. Finally, translate this image back on the x-axis, such that it lies behind the aircraft when seen from a front view. Repeat this process for the side image, but this time, rotate the image 90 degrees around the z-axis and translate it on the y-axis, such that it lies behind the aircraft when seen from a left view. The length of the aircraft's fuselage is 104 centimeters, while the length in the image is 223 centimeters, so we will scale the image by the ratio of these numbers. Finally, set up a top view image by rotating it negative 90 degrees around the y-axis and translating it down along the z-axis. We will scale this image based on the wingspan. The final step to set up the reference images is to adjust the positioning of each image so it matches the model. We will do this as we model the wing. We will now begin modeling the main wing. In SIMNET, the wing geometry is parametrized using multiple segments, each one with its own length, chord and sweep, twist, dihedral, and airfoil. If the wing has control surfaces such as ailerons or flaps, each control surface must be placed within a single segment. Therefore, for this wing we will use 3 segments, one for the central span of the wing, one for the span with aileron, and a third for the wingtip. Add a wing component using the editor pane. Set the viewer pane to top view, and activate the interior display. This will make it easier to adjust the wing geometry relative to the reference image. Adjust the reference image location to match the wing. Before continuing, use the design table in the editor pane to adjust the span, chord, and sweep of each segment to match the reference image. Next, let's assign the proper airfoils to our wing. Add an airfoil component to your design. Go to edit that airfoil and give it a name. Now you can use the database table to select the desired airfoil. SIMNET includes a database of over 1,000 airfoils to choose from. Go to edit the wing and assign this new airfoil to all wing segments. Alternatively, you could use different airfoils along the span. Now that the main wing is mostly modeled, we can use it to adjust the positioning of the front and side reference images. If the wing has dihedral, use the front view to adjust the dihedral angle of each segment. You can set the wing incidence angle by rotating the wing around the x-axis using the rotation table. Let's set an incidence angle of 1.5 degrees. Next, let's set up the control surfaces. Add a servo for the right aileron and place it in the correct location. You can easily create the left aileron servo by creating a lateral copy of the right aileron servo. Using the wings design table, assign each servo to their corresponding wing segments. You will see the control surfaces are automatically created once you assign the servos. Then you can adjust the control surface sizes to match those of the aircraft. We can repeat the same process to create the horizontal stabilizer. We will create the vertical stabilizer by creating a copy of the horizontal stabilizer, rotating it 90 degrees around the x-axis, and adjusting its geometry. We will now model the fuselage. The fuselage geometry is also parametrized using segments, where each segment has its own width, height, roundness, and tilt. Starting with the top view, create multiple fuselage segments and adjust the length and width of each segment to match the geometry of the fuselage. When finished, move to the side view and adjust the height and tilt of each segment to match the reference image. Finally, use a perspective view to adjust the roundness. You can model the motor struts using structural components. Create a new structural component and use the mouse to position it. Use the editor pane to enter the correct dimensions of the component to match the front, side, and top views. Since the left motor strut is identical to the right one, we will create the left strut using the designer pane's lateral copy feature. We can now adjust the color of the fuselage and wing components to finalize our airframe. We can now add the propulsion system, starting with the battery. Use the editor pane to enter the battery specifications, which consist of the number of cells, the capacity, and C rating. You may adjust the battery shape using the width and height parameters. The battery's specific energy and internal resistance are automatically calculated by SIMNET based on these values. However, this aircraft uses a high-performance battery which has higher specific energy. Therefore, we will disable auto-update for the specific energy and enter its value manually. The forward flight propulsion system consists of a brushless motor, propeller, and speed controller. Begin by adding the motor. SIMNET has a database of brushless motors which we can use. Since our specific motor is not found on the database, we will enter the motor's kV rating, maximum current, diameter, and length. Since the manufacturer did not provide the no-load current, voltage for no-load current, and internal resistance of this motor, we will let SIMNET estimate these values for us by leaving the auto button activated for these cells. Next, let's add the propeller. Using the database is the preferred approach, as it relies on highly accurate wind tunnel test data for the aerodynamic modeling. Since our propeller is not found on the database, instead we will enter the propeller specifications manually. We must select the geometry profile that best matches our propeller's geometry. The sport geometry is a propeller with a thin, even chord distribution, which is typically used for high-speed and high-thrust applications. The slow flyer geometry is a propeller with a wide chord distribution which is more aerodynamically efficient and is typically used for slow or hover flight conditions. The thin electric is an intermediate between these two. We will select the thin electric geometry, as it best matches the geometry of the actual propeller. Finally, enter the propeller diameter and pitch. Next, add a speed controller component and set its current rating. Now that we have added the motor, propeller, battery, and speed controller, we must connect these together using the connections table on each of the components. Finally, place the components within the airframe. Repeat the same process for the 4 vertical lift units. In this case, rotate the motors 90 degrees around the y-axis to make them point upwards. Once we create the first unit, We can create the other three by copying the components and modifying their names, locations, and connections. Now that all the aircraft components have been modeled, we will focus on the aircraft's weight and balance. SIMNET automatically estimates the mass of each component, as well as the resulting aircraft mass, inertia, and center of gravity location. However, if you know the exact mass of any component or the aircraft, you can always enter them manually. For the wing, fuselage, and structural components, we must specify the material and type of construction being used. SIMNET uses this information to estimate the mass and inertia of the components. Note that since SIMNET does not know the detailed structural design of the airframe, the mass estimation is a first-order model. If you know the exact mass of one component, you can turn Mass Auto Update off for that component and enter the mass manually, or you can adjust the estimation using the mass margin parameter. For this aircraft, we will select a monocoque fiberglass construction for the wings, stabilizers, fuselage, and motor struts. We will now focus on the total aircraft weight. SIMNET automatically applies a mass margin of 25% to account for other sources of weight such as cabling and fasteners. For this aircraft, we know its total mass to be 6.4 kilograms, so SIMNET is slightly overestimating the weight. We will adjust the mass margin down to account for this. Next, let's look at the center of gravity location. You can turn on the center of gravity marker in the viewer pane to see its location, and you can see the exact position in the editor pane. SIMNET is predicting the center of gravity to be in this location. We can shift the center of gravity location by moving the battery. Alternatively, we could disable auto update for the center of gravity and enter its location manually. The last step before we can simulate the aircraft is to set up the flight controller. Add a new flight controller component and place it in the desired location. Since this is a VTOL aircraft, use the editor pane to load the VTOL flight controller from the database. You can click on the Read User Manual button to obtain detailed information on how to use and configure your aircraft for this flight controller. This consists of connecting all aircraft servos and speed controllers to the appropriate channels of the flight controller, making sure the propellers are spinning in the correct directions, and then tuning any flight controller parameters as required. Let's start by connecting the servos and speed controllers to the appropriate channels. Use the connections table to connect these to the correct flight controller signals. If you are unsure which signal to connect to, read the flight controller user manual for more details. Next, we need to check the propellers are spinning in the correct direction. According to the flight controller manual, the front right and back left propellers must rotate clockwise, while the front left and back right propellers must spin counterclockwise. Use the editor pane to set these propeller rotation directions. Finally, we can start flight testing and check if the flight controller needs tuning or adjusting its parameters. Open a simulation pane alongside an editor pane to edit the flight controller. The default parameters of the flight controller are adequate for most aircraft, but you may find that your aircraft may require some tuning of the PID to provide a more stable flight. This concludes the current tutorial.